recording and then share screen. And we are going to continue our discussion, okay? And if you recall, last class, we started discussing about recursion. Okay, for a recursive method, it is a method call itself. And it needed to have two cases, okay? Base case or stopping case, or sometimes you may also say the word called anchor case. That's how the call itself going to be stopped, okay? So that's one case. The other is the recursive case. But with recursive case, you must have reduction, okay? Reduced call. Okay, generally speaking, when we say reduce, it's reduced parameter call, etc. And that's going to make the method can call itself again and again, okay? So that's general constituents of a recursive method. And regarding efficiency, so if we compare recursive versus, we call it iterative. So iterative is just what we already learned, the loop, etc. Then recursive is not efficient. Why is it not? Because it involves function call overhead, is it? Method call overhead. Okay, method. And but why then do we still need recursion? It's just because sometimes some task cannot be achieved without a recursion concept. Okay, so we do need also the recursive method. And but if a task can be implemented using iterative way, and general recommendation is you implement using iterative implementation. Okay, like last time what we discussed, is it like the factorial calculation, power calculation, Fibonacci calculation, that those still iterative implementation is better, okay? So that's the idea, okay? And within the recursive method, is that the reduction part. The reduction part is like for our binary search case, is it? So if the data involves, so if your task involves a range of data, so task involved a range of data, so normally a range of data we can describe using array or array list. We have learned this, and we also learned stack, that there are more kind of data structure, okay? So anyway, with some range of data, Then normally when we discuss the reduction, that means the range is going to be reduced. That you reduce the range, and then you gradually get the range back to like size 1 or something. That can be at the base case. Okay, that can stop. So that's recursive. But once it reaches the base case, if you recall for the recursive, how it really works is, then it's traced back to your call. Okay, when you call, generally speaking, it's not the base case. So it doesn't know the answer. So it's just keep calling until it reaches the base case. But for base case, you know the answer. Once you reach the base case, you know answer, then you can prop it back, all the way to where you place the call. The place to call is then you roll back, then you can find the answer. Okay, because all then intermediate result can be stopped or can be calculated from the previous call, etc. So that's the general idea, okay, regarding recursion, okay. And what the last example we haven't discussed in this recursive discussion is some kind of game. It's very interesting, okay. So the game is called the Tower of Hanoi. And with this game, if we don't use recursive concept, then probably it's almost no solution, okay. But if we use recursive concept, then we will see the concept, then it's straightforward, okay. So let's see what the idea is. So the idea is you have 3 packs. Okay, suppose we call this as a source pack, and this is auxiliary pack, and this is destination pack. So anyway, something hold plates. Then we have a number of plates. They are not the same size, okay? So their size is different. And they are being placed on the source pack first. Okay, so those are the plates. Different size. Must be different size. And on the source pack, they are placed 1 by 1, okay? But bigger one is below smaller one. Okay, so we must have this condition. Okay, and assuming over here you have n number of plates. Okay, then the game asks you to move all of the plates. Okay, from source to destination. Move all of the plates from source to destination. But there is a condition is each time you can only, so each time moves one at a time. But there is also a condition is you cannot have bigger one on top of smaller one. So you cannot do that. Okay, so that's the all regarding the game and the rules. So we want to move from source to destination. Each time you can only move one, but you are not allowed to get the bigger one on top of the smaller one. But there is a spare pack. We call it auxiliary pack that you can borrow to use. Okay, you can use it for all of the intermediate moves. Okay, and so then how we think about this problem? Then if we think it like this approach, so we get the top n-1. Okay, so we move the top n-1, put it to the auxiliary, the spare one. Okay, so this is the top n-1. Okay, and you move them to the auxiliary. So this is kind of the auxiliary, you treat it as a destination, is it? So the top n-1 can temporarily be stored on the auxiliary one, is it? And then after you move that, then the top n-1 is gone, is it? It's gone, and then you only have the largest one. Because you only have the largest one, then I can move the largest one to the third one, is it? To the destination. Okay, so the largest one is placed at the destination, is it? And after the largest one is placed at the destination, then this source one is empty out, is it? So this empty out, so this can serve as auxiliary. And now the question is how you get to the top n-1, move to the destination with this source as auxiliary, is it? So the problem then change. So the logic, the thinking logic is you assume the top n-1 already moved from the source to the auxiliary. Then at the source, you only have the largest one, that single one, then you can just have one step be moved to the destination. Is it? Now then the question changed. So basically the question got reduced. So it's reduced regarding the top n-1, is it? Reduced from n to n-1. And then for this n-1, how are we going to move it to the destination following the game rule? Is it? Then we can do the same thing. Is it? Then for this top n-1, then you can treat the top n-2. You just think of them together, is it? And move it to the auxiliary. Is it to the auxiliary? Then over here, it only have the largest one. Then you just have one move. Move it to the destination. Is it? So then now this one be cleared again. So now this one be cleared again. So this is the top n minus 2 now. The problem reduced, is it? So problem again reduced to n minus 2, is it? Then similar idea, is it? Then what we can do is we assuming this top n minus 3 moved to the auxiliary, is it? And this is the largest one, then it's being moved to the destination, is it? So we can keep doing like this, okay? So over here, then you just, each time you just assume, but as to how to do that, is it? And we don't need to worry, is it? Because then we can trace back step by step, how are we going to move, okay? So generally speaking, then regarding this game, the idea is that, so when we write the game, how are we going to do Tower of Hanoi? Initially, we have M pack, okay, different size. So we have the source pack, the destination pack, and the auxiliary pack, is it? And we already see if we have one, is it? Then we just move that pack, is it? Move that pack from the source to the destination. If your pack has only one, if you recall, we assume the top n minus 1 or n minus 2 or n minus 3 already moved to the other pack. As to how, we don't need to worry. You just assume, then you only have one, is it? And then that one is going to be moved from source to the destination, is it? From the source to the destination. And this is a stopping case, is when n is on, when you only have one pack, is it? Then you just move from source to destination, is it? Otherwise, what we assume is the top n minus 1 is going to be moved from source. Destination is the auxiliary. The original destination serves as auxiliary, okay? So we switch role here, is it? You switch. So auxiliary change to destination, and the original destination change to auxiliary. We switch the role here, is it? Then we only have the largest one. That largest one, you just move it from source to destination, okay, to destination. And after you finish that step, then you needed to get to the top n minus 1, is it? Plaque from the auxiliary. So this time, this auxiliary serves as source to the destination. And that source one, this time serves as auxiliary. So this time change role again, is it? So over here, then we can complete moving all of the plate, okay, from source to the destination. So over here, we have one stopping case, is it? And over here, we have two recursive case, okay? So this is recursive, and this is also recursive. Okay, so that's how we use a recursive concept. Then you can play the game. But then you may ask, then how do you get to the top n minus 1 move? Is it? Then when it reaches the stopping case, it will prop back, as previously we learned. So basically, when we run this program, it will tell us step by step how you move the plate, okay, the plate. So let's take a look how it works. We can run this program. Let's see the main part. Okay, we have five plates. Okay, then we have three towel. Okay, three pack. So let's see how it moves after we run this program. And did you see the running result? Then it will tell you step by step how you move each disk. Okay, and you can see the disk is going to be moved a number of times, is it, until it's settled to where it is it? And you can see the first plate is going to be moved to the last. Is it the last step to be moved because this is the top one? Is it the top one? And the largest one, even for the largest one, the plate number 5, is it? It's being settled down to its destination at this step. But before this step, we can also see is it before the largest one being moved. So this is the largest one be settled down to the destination one. But before it, is it involves all of the steps to move all of the top four plates being moved among the source, the destination, and the auxiliary, a number of steps. Is it before the last one? Okay, so basically all of these steps, it involved the top n-1. How do all of them get to be placed on the temporary one? Is it on the temporary one? How all of them get to be placed step by step so that it also won't violate the game rule? Is it no top one be placed, or no bigger one be placed on top of the smaller one? Is it? We can also kind of tracing here, okay, following what it shows step here. Is it? So we have A, and in this case, C is the intermediate one. Is it? B is the destination. Is it? So initially it's 5 is here, and 4, and then 3, and then 2, and then 1. Is it? So here is that 1 be moved to B. Is it? So here 1 is. Then to move 2. Is it? 2 move to here because you cannot move 2 on top of. So 2 is here. 2 is here. Is it? And then we move 1 again. Is it? Move 1 from B to C. That's 5. Is it? So 1, 2. So that's still following the rule. Is it? Then you move 3 from A to B. So now this is 3. Is it? This is 3. And then you move what? Then we move 1 from C to A. Is it? So we are going to move it back. 1 is back here. Is it? And move 1 back from we are here. Move 1 from C to A. Is it? Then we move C, or move 2 from C to B. So here is 2. Here is 2. Is it? We move here. Okay. Then you move 4 from A to C. Is it? So now 4 is here. Okay. So we do this step by step. Is it? Then each time it follows that game rule. Is it? And until here, is it? You get the 5 to the destination, and of the others, the top n minus 1 going to be at the temporary, and here is number 5, is it? So, but that's how, when we think about the program, is it, as to how each play is placed, we already, so the program gives you step by step how you place the plate so that you can play the game. Is it? Okay, so that's the idea about this towers of Hanoi. Okay, so basically we also completed the study of recursion. Okay, so the concept is not too complicated. Okay, but it may take time to get used to it.